We want to look at binomial probability. Now, the idea of binomial probability is obviously using the binomial theorem, and where this comes in handy of using the binomial theorem in probability is where we have a situation where there's only two outcomes. So it's the either or, say, situation happening. Really complementary events lend themselves very well. Now, the binomial theorem part comes in when we have that event occurring more than once, and the more times it happens, obviously, the more useful the binomial theorem is going to become. So that's where we're going to use binomial probability. Two outcomes in our situation, either something's going to happen or it's not going to happen, so complementary events, and that event occurring more than once. So let's have a look at the first one. A coin is tossed 12 times. So what's the probability of tossing 5 tails? Now, those 5 tails can occur anywhere. Now that's in case you can have the 5 tails occurring first, then 7 heads. Or then you can have 4 tails and then a tail occurring somewhere in the last 7. So there's a lot of different ways you can find that. Now the idea of the binomial probability is to have us look at the probability there where we have half as for heads and half for tails. We know that's the probability of tossing a coin. So really when we look at this, the half for the head, so probability of getting a head and the probability of getting a tail, if we explored it, we could write that as a binomial expression to the power of 12 because we're tossing it 12 times. So we could have the 12C0 representing no heads and 12 tails. So 12C0 would be no heads. 12C1 would be 1 head. 12C2, 2 heads. All the way through to 12C12, which would represent 12 heads. And we could start to work out the probability that that would occur. So you can see how we start to apply our binomial theorem and the general expression in that on each term. So if we take it just for this one situation, because the 5 tails, or which would be 7 heads, which would be one of these parts of the expression, one term in the binomial expansion. The one that we want is where it's got 5 tails, and we've got 12C5 there. So it means we get a half to the power of 7, because that represents the probability that you get the 7 heads, and the probability that you get the 5 tails. So we get that representation, and that would occur 12C5 times when we did that expansion of a half plus a half to the power of 12. You would see 12C5 lots of the half to the power of 7 and half to the power of 5 and collect those terms. That's how many you would get. Now it wouldn't matter if you wrote 12C5 or 12C7 there, because remember the nature of the Pascal's triangle and that notation, the symmetry effect. 12C5 is the same as 12C7. So don't panic about that too much, what you write and where you write the probabilities so much. So there's where we go. We've applied the binomial theorem. We can calculate it. We get 0.1934, which sounds about right. So let's have a look at this one where we got 2 or 3 heads. Well, that would occur. 2 heads would be 12C10 or 12C2, whichever way we want to do it. A half to the power of 2 and a half to the power of 10. So the heads are to the power of 2, tails to the power of 10. And 12C9 or 12C3, either way, that's the same. Half to the power of 9 would be the heads that'd be tails there. That'd be 9 tails and 3 heads. So 2 or 3 heads can come out that many ways. At least 10 tails. Again, looking at our language here, if we get at least 10 tails, it means we could get 10 tails, 11 tails, or 12 tails. So we can treat this as 12C2, 10 tails and 2 heads, 11 tails and 1 head with the 12C1, and 12C0 would be 12 tails and no heads. Remember, that could be written as 12C12, 12C11, 12C10. Would work out exactly the same. Another problem. We've got a problem with a certain brand of stereo being faulty as 1/12. So that's either faulty or not. So if it's faulty, probability is 1/12. Probability of not being faulty is 11/12. So if the store buys 8 of the stereos, what's the probability that 3 would be faulty? So 3 would be faulty out of the 8. That would leave us with the probability that you get non-faulty stereos being 11 on 12, and we want 5 of those. Where the faulty stereos, the probability there would be the power of 3. So again, if we wrote 8C5, wouldn't be a problem. We want to leave our answer in index notation, so that gives us 11 to the power of 5. 12 to the power of 5 times 12 to the power of 3 is 12 to the power of 8. So we can write like that, and 8C3 is 56. So 56 lots of, that would give us our probability. This time we got a certain strain of tomato plants has 2/5 of a chance of producing a miniature tomato. So if 4 of the plants are grown, so you can see how we're getting a multiple event occurring. 2/5 of producing miniature tomato, 4 of the plants. What's the probability that all would have a miniature tomatoes? Well, we could write that as P, the probability of 4 miniature tomato plants. 2/5 to the power of 4. We could have 4C0, or 4C4, which is 1 anyway. So really we're looking at that as a 2-unit probability question there. This time though, 2 have miniature tomatoes. So we can get that 4C 2 ways, and 2 would have a miniature tomatoes, which have a 2/5 chance, and 2 won't have miniature tomatoes, which had 3/5 of chance. Do that calculation on the calculator, gives us 216 on 625. At least 1. So if it has at least 1 out of the 4, means there's 1 minus the probability that we get none. So it'd be 1 minus 4C0, which is 1. 2/5, so there's not going to get any plants there. So the 2/5 to the power of 0 and 3/5 to the power of 4, doing our calculation. Probability that we get at least 1 is 544 on 625. This time we have a department store with 6 entrances, and 5 people arrive at the store at a certain time. What's the probability that all 5 people use the same entrance? Well, using the same entrance, well, they've got one, they're all different entrances, so they've got 1/6 of a chance to use a particular entrance. So using that entrance, 5C5, 1 on 6 to the power of 5, you've got 1 in 7,776 chances that they would do that, because that's the amount of different ways we could do it. Probably the power of 4 this time, use the same entrance. The other person uses a different entrance. Well, 5C4, we would get probably 1 to the power 1/6 to the power of 4, and 5/6 to the power of 1 equals 25 on 7,776. What's probably that all 5 use a different entrance from each other? Well, we can look at the problem this way. One person would use the first entrance, then the next person has 5/6 of a chance to use the next entrance. The next one has 4 out of 6, 3 out of 6, 2 out of 6. So that gives us 5 factorial over 6 to the power of 4, or 5 on 54 is our answer there. Question 4, we've got a bias coin, and the probability of a head is 0.3. So we toss it 4 times, probability of getting 3 heads. So probability of 3 would be 4C3. Probability of getting a head is 0.3, so it leaves the probability of getting a tail 0.7. And we get 3 heads and 1 tail. And the probability of getting that situation would be 189 on 2,500. At most 3 heads, which means, well, we could get no heads, 1 head, 2 heads, 3 heads. Anyone that's not included there is the probability of getting 4 heads, which is 1 minus the 0.3 to the power of 4, which gives us that our answer there. This time we got a sample of 5 items taken, and we know that 10% are defective. So there's our probability. Multiple samples, multiple events happening. So what's the probability we get all defectives? So the probability of all defectives would be 5C5, 0.1 to the power of 5. There's only 10% of the chance to get the power of 5 defective. And the 0.9 to the power of 0, which is 1 on 100,000. Probability of no defectives would be 5C0, 0.1 to the power of 0, 0.9 to the power of 5, which gives us something more reasonable, 0.590 over 0, 0.95049. And then show the chance that our sample contains more than 2 defectives. So more than 2 defectives, well, because there's 5, it's probably just as easy to go. I don't think it'd work either way. You can work it either way. I think it's probably the same. 1 minus the probability that you get 2, and then 1, and then no defectives. So it gives us 1 minus 5C2, the 0.1, 10% chance, power of 2, 90% chance to the power of 3. One defective is your 10% to the power of 1 and your 90% to the power of 4. And no defectives, as we saw, was the 90% to the power of 5. Do our calculation. There we get 0.00856, which is less than 1%, which is what we need to find and show. This time we got a probability a certain breed of dog will have black spots is 2/5. And if a multiple events of 5 pups occurring, probably that you have 3 with black spots, well, it's 5C3. 2/5 of a chance to get the probability and is of black spots, and that occurs 3 times. And we've got 2 without black spots, which has a chance 3 and 5 chance. So that leaves us with 144 on 625. None will have black spots. Well, 5C0 to the power of 5, because that's probably it will have spots to the power of 0. Probably it doesn't have spots to the power of 5. So there's our answer there. 4 will have black spots. So P4, 5C4. Then will be 2/5 to the power of 4 and 3/5 to the power of 1. And at least 3. Well, at least 3 would be probably 3, 4, or 5. And there's our answers there. Fewer than 3. Well, if it's either at least 3 or fewer than 3. So that's where we get our complementary event occurring there. And the last question here, we've got a school owns 12 data projectors and 8 smartboards. Find the probability of a data projector being used in a certain period is 3/4. Probably a smartboard being used in the same period is 5. What's the probability of 3 data projectors and 5 smartboards being used at the same time? Well, we've got 12C3, and so 3 data projectors being used out of 12. Well, we've got 3/4 of a chance to the power of 3, because there's only 3 data projectors being used, and that means it's 1/4 to the power of 9, because it's probability it doesn't get used. We want n there, so it shouldn't be addition, it should be multiplication there to give us our calculation, because and it means we've got to have both of them occurring, so it's a multiplication. Probability of a 5 smartboards being used, well, we get that 8C 5 ways. So our probability of a smartboard is 5/6, so we put that to the power of 5. And the probability it isn't being used is 1/6, so we put that to the power of 3. And then do our calculation. It says leave it in index form, so we can leave it as 12C3, and the 3 cubed over 49, and the 5 power of 5 over 6 power of 8. Really, that's what we're interested in. Can you get it to there rather than more that? So there we go. That's where binomial probability. Looking at ideas that you can apply, have a situation where you could apply a binomial theorem, where you would have a complementary event occurring. So either something's occurring or it's not occurring, and it occurs multiple times. As I said, very handy to be able to use binomial probability to solve those type of problems. And all we're doing is really applying our binomial theorem to the given situations, depending on what the problem's asking.